Any doubts so far?
Oh, sir.
Oh, sir.
Let's wait for some time. Let others join in. So next we'll be combining having two resistors instead of one. So here also if R1 and R2 are different, you have to choose this known resistance such that the balance point is in the middle, approximately in the middle. Okay, suppose R1 is 20 means this value you should choose approximately 20. If R2 is 30 means this value should choose approximately as 30. Okay, so this value does not matter because as long as it's known, it doesn't matter what value you choose. Okay. So here in this case, you have to do this experiment thrice. First one with only R1 without this R2. But while drawing the diagram, we put both just to convey that for the series experiment. But first, when you're doing this, remove this R2, only R1. Second time, only this R2. Third time, it's both in series. So whatever you did the previous time, this time you have to do it 3 times. One with R1, okay, 3 readings. Previously, I did 5 readings. But since you have to do it thrice this time, so reduce the number of readings to 3. Okay, so this reading can repeat by changing R a little bit. Once I get the balance point of course in the middle, from that value of R, increase R a little bit and then decrease R a little bit so that this thing is approximately in the middle. Second time for R2 and the third time for R1 plus R2. So if I take this reading here, the mean value and this one, if I add those two, I should get this one. That way I'm verifying this is true. Okay, so this is the verification of this experiment. So So here, for this one, I need two resistors, right? So first I'm using one resistance, one rheostat. Okay. So for the second, I will do the different rheostat with different value of the resistance. Okay. Once I should not move this knob after I use it in X1 because the resistance value will change. X1 should be X1 only. Second, this is X2. And then I'll connect these X1 and X2 in series and take the third set of readings. So this circuit you can understand it. It's same as the previous one. This is the meter bridge and this is the voltage source. So the positive term of the voltage source will enter one end of the rheostat. And the other end of the rheostat will connect to the end of this meter bridge. So positive term of this thing is not clear here, but obviously if you go to the lab, you can see. So it should be like one end of this thing is coming here, and the other end of the rheostat, maybe at the top of the bottom, will come to this other end of this wire here. So the full voltage is dropping across this 1 meter wire of the meter bridge. This is the voltage source here, they are put on the top. So positive terminal is connected to one end of this 1 meter wire, and the negative terminal they have put it on the other end of the meter wire. And here there should be a rheostat to be safe. You will damage this one. So that is the rheostat. Okay, and I put in the middle so that at least 15 amps is there in the circuit to protect this voltage source. And in one gap, you have the standard resistance box. Another gap I have is unknown resistance. First, I'll put the first one X1 and find X1. And second, I'll put X2. I remove this X1 and put X2. In the third case, I'll connect this X1 X2 in series and then connect this end here and connect this end here. So X1 plus X2 is coming in this gap. And then repeat the experiment for that one. Okay, result is within the, I verified the law of So basically you have to find R1 value from this here. Okay, second one R2 here. So this is 20 and this is 30. So this should come out to be 50. Okay, that way I'm verifying R1 plus R2 is R1 plus R2 only. So any questions? If not, we
Sir,
can,
how to find the separate R1 and R2 resistance, sir?
yeah, for R1, I just have to connect this X1 only. I have to remove this,
Okay, separately we are connecting X1 and
this one won't be there. Only this,
okay, sir.
but the diagram they shown both because I don't know, I just have to show one diagram, no? Here both are there. This is the third set of readings. This diagram corresponds.
That's the R1 plus R2.
Third set of readings.
Okay,
First, it is remove this R2. Okay, connect this thing directly here.
okay, sir.
So only R1 will be there. Second set, remove this R1 and connect this end here. Only R2 will be there. Third one,
Okay, sir.
R2 and connect this end here and this end here. So three set of readings.
Okay, sir.
Any other question? Okay, this is the fourth experiment or the first set. Okay, so here, this is the voltage source. This one, okay. So here instead of having a rheostat, I'm having a resistance box. This is a huge resistance. Rheostat is just 30 amps, but this can have up to 3000 amps or something, even 10,000 ohms. So we are safe here. So one end of the positive terminal of the voltage source. Okay, here I connect with the ammeter. See, this positive terminal is voltage source is entering this ammeter, and the negative end of this ammeter is going to the resistance box. Okay, one end of the resistance box, and the other end of the resistance box, it's coming out. Yeah, it's coming out connected to this galvanometer. This wire. Okay, and the current that's coming out of the galvanometer is going through this. Okay, so you can actually close. Okay, so this negative end of this galvanometer is going here and closing with this voltage source. So the series circuit is clear. I'll just redraw it again. So the current coming out of this positive terminal of this voltage source is entering this ammeter. Okay, and the current leaving this ammeter, that's from the negative terminal, it's entering this resistance box. One end of the resistance box. Other end is this one. Hello? I just come in 2 minutes. Yeah. So current coming out of this galvanometer is entering this resistance box, one terminal, and the other terminal, it's here. And the current coming out of the resistance box is entering this galvanometer, and the current coming out of the galvanometer is entering this voltage source. The negative terminal. Is it clear? I'll explain this other two later. Okay. So current out of the galvanometer, sorry, this voltage source is entering this ammeter, and out of the ammeter is entering this resistance box one terminal, and it's coming to the resistance box and entering this galvanometer. So the current in this circuit is measured both by this ammeter here and the galvanometer here. Both should correspond to the same current, right? Because same series circuit. Okay, this is a voltmeter. This voltmeter is connected across this galvanometer to measure the voltage drop across the galvanometer. So this is the voltmeter. Positive terminal is connected to the positive of this galvanometer. Okay, and the negative terminal of this voltmeter is connected to the negative of this galvanometer. So this voltmeter is measuring the voltage drop across the galvanometer. You will know why it is connected like that. So connection is clear. Okay, so with this, I can have a small voltage here and a huge resistance here, so that galvanometer is basically sensitive instrument. Okay, and this ammeter, it's milliammeter. It will measure milliamps. Okay, so if I reduce the resistance of this box, I can get the full scale deflection of this galvanometer. Okay, and I can measure the corresponding current here. From that, I will know what is one division of this galvanometer correspond to. See, galvanometer will be marked in divisions. It won't be amps. Ammeter will be measured in amps. If you look at the galvanometer, it will be like this. The middle one will be 0. Okay, and then there will be divisions, 5 divisions, this 10, like that. Okay, so it will be in divisions. And here will be 5, 10, whatever, 20, like that. Okay, but if you look at the ammeter, this galvanometer, if you look at the ammeter, it will be in amps. That is the job of ammeter, right? It should give me current. Here it's milliammeter. Okay, so here will be whatever, just I'm saying, for example, 3, and this will be 1. So this 3 means it's 3 milliamps. Okay, here 30 means 30 divisions. And what does one division correspond to, that you have to find out. Okay, so now I'll adjust the resistance such that this, I have a thing at this point. So this is a full scale deflection. And what is the amount of current that will measure from this ammeter? So if the full scale deflection, suppose this division is say 30, and the current is say 0.6 milliamps. So 0.6 milliamps gives me full scale deflection of 30 divisions. Okay, so one division corresponds to 0.6 by 30 milliamps per division. This least count, here it's also called K of the galvanometer, which corresponds to the amount of current for one division deflection. Okay, so this first thing you can measure. After that, suppose this obviously 0.6, I just did the experiment in the lab and it came out to be 0.6. Obviously 0.6 milliamps is a small value. But suppose I want this galvanometer to measure high current. Say I want to measure up to say 3 amps. Okay, that I can do by diverting some current that's entering this galvanometer into a parallel branch. There's a parallel branch. See this rheostat, I have connected parallel to this galvanometer. Okay, positive terminal is here, and the negative terminal of this galvanometer is connected to the other end of the rheostat at the top. Okay, so now the current will enter here and go through this much amount of resistance and enter this one and come out of this one. So the amount of resistance which is connected in parallel to this galvanometer is this part, corresponding to this part. Okay, so if I keep this thing value small, then lot of current will get diverted in this parallel branch. The current that is coming here, here, now it has got two paths. One is through the galvanometer, other one is through this rheostat I connected here, this shunt resistance. Okay, so whatever is the current, will get divided into two, and this value of the shunt resistance is small. lot of currents will get diverted here, and only a small amount of current will get in this galvanometer. So obviously the galvanometer is showing a full scale diffusion of 0.6 milliamps. Okay, so when 0.6 milliamps flows through this galvanometer, the remaining 3 minus 0.6. Okay, let me make it reasonable. Let me say I'm converting to ammeter of measure up to 3 milliamps. So remaining 2.4 milliamps should pass through this shunt. Okay, so this way I'm converting this galvanometer into something which can measure higher currents. So this whole combination is the ammeter. This combination of this galvanometer plus this parallel shunt resistance, this is ammeter. Okay, so okay. See, the resistance of the galvanometer is, say, RG or G, resistance of the galvanometer. That I can find out by, I know the current corresponds to the full scale deflection, right? It's 0.6 milliamps. And I know the voltage of across this galvanometer by this voltmeter reading. Okay, so using the voltmeter reading, whatever is the volt, okay, this will give me the value of the resistance, galvanometer resistance. It's also represented as symbol G. Okay, so once I know the galvanometer resistance, and I want to increase this current in the ammeter to 3 milliamps, I can find the corresponding shunt resistance value, which will give me that value. So when this current is going through these two branches, the drop across this galvanometer, which is Ig into G, should be equal to I minus Ig into shunt resistance R S. This current is the total current, which is I. Okay, this current which is centering the galvanometer is Ig. So the remaining current here, it's I minus Ig. So the drop from here to here across this galvanometer is Ig into G. Okay, and the drop across this shunt resistance is I minus Ig into S. Yes, the shunt resistance value. So those two should be equal. And current in the galvanometer is known because it corresponds to full scale deflection, which I found previously as 0.6. Okay, and this is the desired value of current, which they are given as 3 milliamps. Okay, this is known. From this I can find, yes, I can find from here. Okay, so once I design this, yes, once S is known, I can find the current for any other division. And that current will match with the current value of the current here. Okay, now this I'll explain maybe later. Yeah. Now this one. Okay, I will have it here. Okay, this experiment I'll come back to it later. We'll move the other one. So what is this experiment? Make a guess.
The concave mirror.
Yeah, concave mirror, because light source is here, this one, and I'm having a screen here. So obviously the light should go like this and come back like this, right? So there is a reflection here. Okay, so this is a concave mirror. So U is this distance from here to here. Okay, and this distance is V. Okay, so to find the focal length, I have to use this formula 1 by U plus 1 by V equal to 1 by F, right? So concave mirror, aim is to find the focal length. Okay, using different, that's UV method. Okay, so once for this experiment, for the previous one, you should have a circuit diagram as soon as you have the experiment. But here you should have a schematic diagram. This is a schematic diagram. This is a mirror. Okay, and this is the object, and the image will be like here. Okay, so here my object is this one. This is my object. Okay, which is the light source, and this is the screen. Okay, so the screen is here, and the image is formed here. Okay, U is the distance between the object and the mirror, and V is the distance between the image and the this one. So here, once you get a proper image, you can adjust this, move this mirror say a little bit here. So that way I'm decreasing U. Once I decrease U, V will increase. So this have to move further out. Because 1 by U plus 1 by V equal to 1 by F. So if it decrease U means this term will increase. F is a constant. So this term increasing, this term has to decrease. If this term is decreasing means V has to increase. So basically U and V have opposite relation. If U is decreasing means V has to increase. So if I try to move this, once I get this one reading, for the second reading, if I move this thing a little bit here, you should expect this screen to move a little bit farther away so that V is increased, because U is decreased by moving it closer. So V has to increase so that I get the focal length fixed, right? So obviously, so you can get different readings by adjusting different for different using different values of U. So this is how the table will look. U, okay, and then V have to measure, and then you can find the focal length using this formula. It's basically 1 by F equal to 1 by U plus 1 by V. You can rewrite like this. Everything is in centimeter. One thing I want to say, what was that? There is a scale here. This is a scale which you can measure this distance from here to here. Okay, and one more thing is, instead of this light source, I can use a distance window here, which is farther away, and not here. This is a mirror, right? So obviously I have to move view something which is farther away here, okay, and get the corresponding image here. So that corresponds to U being infinity. So distant object method, you have get an image of a far away object like a window or something. So in that case, U is infinity. When U is infinity, V will be F. Okay, so instead of this light source, try to get the image of some distant object on this white screen. Okay, in that case, this distance, which is V, same as the focal length. So this is called distant object method. So with this, you can get the approximate focal length. After that, you can do this UV method. Distant object method. Focal length complementary this. Okay, this I did using the wall in the lab. You can also use this screen itself. Okay, so since it's a mirror, obviously the object should be on this side only. Okay, so using the distant object, adjust the screen so that I am getting a good image here. So once I do that, this distance is the focal length. Because U is infinity, when you put U equal to infinity in this formula, you get V as F. So that is the first method. After that, you can have different U and V. So this is simple experiment. It's not difficult. The only thing which could be difficult is both U and V are in the object in this screen in the same direction, right? So the light has to go in form of a V. Okay. And one thing, if you look at this object, it looks like a triangle. See, if you look closer, this object they have made as a triangle. So if you ask the Viva question, why is it like a triangle, not a square or something? See, this thing here will look like this triangle. Okay, the light will come out of this one. Okay, so why is it a triangle? Why not have a rectangle like this? Anyone?
Sir, if you show the inverted image, no, sir.
If you have a triangle, if the image is inverted, the image will look like this. So if the image looks like this, we know that the image is inverted. For a concave, it will be inverted. Okay. If the image is object is like this, then inverted, I cannot figure out whether it's inverted or not. Because the image even is inverted, it look like this only. Okay, so that's why they made it as a triangle. This object is straight, no, image is inverted. So if you have a triangle, it will be inverted triangle. Okay, is that clear? It's a simple experiment. Should be happy if you get this one. Okay, next one is convex lens. It's still simpler.
Yes, sir.
Here this is the source, right? So the light will get from the source here. From the source, it will hit the lens. Okay, and after the lens, it will form an image here. Okay, this is the direction of the light. Okay, so this distance is u, and this distance is the image distance v. Okay, so once you get one proper image, you can adjust this mirror a little bit. You can move this mirror a little bit inside. Okay, that way u is decreasing, so v has to increase. So the screen has to be pushed outside to get this good image. I think I'm right. Yes, because the lens formula is 1 by u plus 1 by v to 1 by f. Is it the lens formula?
Sir, minus.
There is a minus sign here. But here I'm actually measuring the distance. Here what I'm actually measuring is minus u. Okay, so by moving this thing inside, minus u has decreased, not u. Because the distance is minus u. See, this is my lens, right? So with this lens as reference, direction of the incident light is positive. That is the convention. Incident light is this direction towards left. So this is my positive direction. And the object is on this left side or on the negative side. So u is negative. So the distance is minus u. So when I move this thing towards like this, the distance is decreased. So what is decreasing is minus u. So minus u is decreasing means this first term is increasing. So this second term has to decrease because the right hand side is constant. So this second term has to decrease. That means v has to increase. Okay. So object distance is decreased. Image distance is increasing. Okay. So second. Oh God, meeting is ending again. Okay. So next thing, if I get here, then the screen has to move out further. Okay, and first image I can get by instead of this using this light source, I can take a distant window here and take the image of this window on the screen. In that case, this V will be F. So first I can get a distant object image. This is the convex lens. This is the ray diagram. Okay. It's different from the mirror. This is the formula 1 by 2, this one. If you're taking u as a distance, then you can rewrite this formula like this. Actually, it's a minus u here. Okay, so here object distance, I'm just not putting the negative sign. Without the negative, it is just the distance. is a positive quantity. In that case, the formula will look like this. Okay, so this is also a simple experiment. Okay, the third one I put is the prism. So this is the prism. You have to place it on the paper and mark the outline like this. Okay, and after that, to this side of the prism, I just have to draw a perpendicular. So you have to make this dot, make it a dot, and the protractor, this is the middle of the protractor. So this middle of the protractor should stand on top of this dot. Okay, that's why you have to put a dot here. And after this line should lie on this line. Okay, so that way the protractor is put properly. After 90 degrees will be here. So mark it as a dot here. So join these two dots, you'll get the normal to the surface. And from that, I have to choose this incident ray. Suppose this ISA 30 degrees, draw a line at 30 degrees using protractor. So once I draw this line, put two pins here. Okay, so this is the incident ray. Now place the prism here, and then from this side of the prism, look at these two pins. And you have to look at the proper angle so that these two pins appear as a straight line. By looking from here, the pins you can see straight without passing the prism. You can leave that. Just you have to look at the image of the prism through the image of this pin through the prism. Okay, and place the third pin and the fourth pin so that all the four pins are on the same line. After that, you can remove this prism and circle these two dots. Otherwise, you'll miss them. So circle the two dots where the pin mark is there, and after that, join them. So this is the emergent ray. And then you can join these 2 points to get the refracted ray. So this emergent ray, if you just extend it on the forward side, okay, and this incident ray on the forward side, and this emergent ray on this backward, this one. So this angle is the deviation angle of deviation. Okay, so this second set of reading can choose by using a different incident ray. Instead of 30, I can choose 35 and place the two pins here, and that will give me a different T value. See, here you can see the prism. Okay, so first you have put 30 and then 35, 40. Okay, so, and then you can find the deviation. This is the emergent ray, the two pins here, P3 and P4. So emergent ray projected backwards and the incident ray projected forwards. So those two will meet. So this is the deviation, right? So the incident ray which is coming here is deviating this much as an emergent ray. So second D2. So, and after that you have to, so the table is this incident ray, you have to change angle and you have to measure this deviation. Okay, so for this particular graph, the minimum angle of I of 47 corresponds to the angle of minimum deviation. So that means 47 is somewhere here. So these readings are, suppose the deviation is say around 30, then you have to take values less than this 35, say 30 and 25. Then you can catch this minimum. Okay, so once I get this minimum deviation, I can find the refractive index using this formula. Oh, they are not done. One outcome of this experiment is to find this angle of incidence corresponding to the minimum deviation. You have to find this I, or you have to find this angle of minimum deviation. Okay, and once I know this thing, I can find the refractive index of the glass prism by using the formula sine A plus Tm. This is corresponding to minimum deviation by 2 divided by sine A. This is the equilateral prism. Okay, so the angle of the prism is 60 degrees. All angles are equal. So A is 60 and dm is got from this graph. Okay, this is the value of dm. This value is not required. So once I get dm from here, so from this I can find the refractive index of the glass. There are two things to find. One is DM, second one is L. This is the fourth experiment. This is the last section of this second part. So this is the p-n junction. Here everything is connected inside. You don't have to do anything. You just have to take this plug point and connect to the main supply. And this is forward bias, the one on the left side. And this is the reverse bias. Okay, they have written it here. This is the forward bias, this is the reverse bias. So you just have to turn it on. Connect this thing to the voltage supply. Okay, and then there is a switch here, no? So turn it on. Okay, and this is the voltage knob. So increase it slowly. First, increase it to get the idea of the full range. So the maximum voltage will be around 0.7 volts. So you know the voltage is varying from 0 to 0.7. So you want 10 readings between them. So you can have an idea of in what step the voltage will jump. So voltage will come here, and the corresponding current will come here. And then you can make this thing 0 volts, and then you have to increase this voltage. So here the voltage will be here, reverse bias. Here the voltage will be here. This one. This is the current here. Okay, here on the reverse bias, this is the current. So this V just above the volts is the reading corresponding to the voltage. Okay, and the table will look like this. Voltage and current. So yeah, here it's varying from 0.2 to 0.2. I think the one which is there in the lab is from 0.2 to 0.7 or something. So first get the maximum value so you can have an idea how much, what division, what steps you have to take the readings. And then find the current. Forward current will be in milliamps. And then you make this thing 0. And after you use this reverse voltage, so I can get the maximum range, what will jump. So in between you have to divide in appropriate steps to get the different readings. And the current will be less in microamps. Okay. And after you have to plot these two. So this was a simple experiment. Forward voltage is varying from 0 to 0.9. Here will be from 5 to 40. So obviously the scale for this right side and left side will be different. Okay, in ohm side is same for a resistor. Here it is different because in forward bias with a small voltage I can get a good current. But here I apply a large voltage to see the variation. Similarly, the forward bias, the scale of the upward one will be in milliamps. Okay, here one division is connected to 1 milliamp, right? Here in this bottom one division is to 10 microamps. So it's much smaller current here. The scale is not uniform. In the sense, it's different for the right and the left, and for up and bottom also. Okay. This is for the reverse thing. Here the scale is for the forward thing. So in the forward thing, 1 centimeter is 0.1 volts. Here it is 5 volts. And the current is 1 centimeter is 1 milliamp. Here is 10 microamps. So this is different compared to a resistor. The resistor does not matter whether it's positive or negative. Okay, so this is the fourth experiment. So we'll close now. And then you send me a message by WhatsApp if you have any doubts. Tomorrow also. Okay, based on that, I'll decide what to do. Okay.
Okay,
sir.
sir.
Okay, we'll get over in